Okay, good morning everybody. Out there is having a wonderful day. So today I'm going to be talking about priority queues and different ways we can implement priority queues. In particular, I'll be highlighting what is called a heap after I get through some of the basics with a priority queue. Now, I'm not sure if you've ever seen or heard of a priority queue before, so I feel like I want to make sure I go through that carefully so that way everybody's sort of familiar with the idea. So I'm going to define for you the priority queue ADT. This is the one we're going to use. So if you've seen a queue before, the easy thing about a priority queue is it's just a generalization of one. So in a queue, you imagine you have a lineup. So imagine you're like Tim Hortons, or you're waiting in line to get to say you're just put into a queue, hence its name. You have a lineup. Each person goes to the back of the line, and every time somebody gets serviced on the front of the line, they go off the front. The next person in line gets serviced next. These are so-called DQ operations. When you put somebody in the back of the line, that is an NQ operation. Now, in a priority queue, the difference here is that we're allowed to have it where the elements have priorities. So each element is going to have two properties to it, a key or priority. I'm often going to call it a key, and it's going to have some value or data. Now, just as a remark, these keys, I'm allowed to have duplicate keys. So two elements are allowed to have duplicate keys. And it must be that when I have these keys, I'm able to list the keys in order from smallest to largest. So they have to be comparable. Typically, when you deal with the priorities, normally they're numbers, typically. So normally you can list numbers out from smallest to largest. It's okay if two have the same value. That's basically what I'm saying. So I want to talk briefly about what kind of delineates the priority queue from a queue, and I'm going to do a couple of analogies here with you. So the big thing is that there's going to be these operations. These are the main ones. As the course progresses, we may add more operations than these ones. So first we have the notion of inserting. This is going to be very much like NQ, except what we're going to do is we're going to create an element. It has key K, value V, and we're going to put it into this priority queue. Now I'm going to show you briefly what I mean by this. Now, in a queue normally, like you can think of a priority queue very much like a queue. There's a couple of ways you can view a priority queue. So imagine you have the front of the queue, and you have the rear. Actually, let me draw it this way. It makes it a little easier to visualize. So obviously I DQ off the front, and then I put elements on the rear. So just think of it like a line, like I'm going to get some Tim Hortons coffee. I don't do coffee, which is kind of weird to believe, but I don't. But what would happen is when I do an NQ operation of the in a queue, what would happen is I would place the element right here at the front, and then if I have another one, I put it behind the front element, and I just keep inserting them from the rear. And as I do DQs, this front one will go away, right? Then I do another DQ, this one goes away. Keep in mind, when I do a DQ operation, I get back the element in question, and so on like this. Now, in a priority queue, what happens instead, this is what makes it a little different, is that, hence its name, each one of my elements is going to have some priority. So imagine I put an element in here and I say, okay, well, it's going to have, so I give it a key and a data. So imagine I have some value v1 and its priority is 1. Actually, let's go 3. Just for fun, let's make it 3. So its priority is 3 and it has value 1. National Coffee Day. Awesome. So if I do an insert operation, this is where it would go, right on the front. Now, this is just a way of visualizing the priority queue for you to connect it up with a queue. So when I do another insert operation, and suppose the priority of this element is 2, what happens instead is the element with the most important priority goes towards the front. So instead of it being this one right here, this one gets shuffled over here. So the 3v1 is here, and now I would have my new element that I'm going that has a smaller value for the priority. I'm going to assume that the priority that is the lowest number is the most valuable one. You can always define a priority queue where the larger the priority, the more important it is. I'm just going to define it as lower the priority, the more important it is. So there's a couple ways you can think about this. If you think about it like a line, is, for example, if say, just as a topical example, if you think about it in terms of triage in medical settings, a priority queue is very natural to think about how you would help patients that come into a hospital, for example. For example, somebody that comes in, they say, hey, look, I sprained my wrist, versus someone, I cut my arm off. You probably want to have somebody that cut their arm off go in first. That's a higher priority case. So in triage, very often, a priority queue is much more natural than analyze and use for when you're dealing with patients, right? So another setting is like, say, if you've ever been to a government office, very often they like to queue you using line, like they give you a number. So if they see you once, they may ask you, hey, look, can you fill this out? And then they may give you like a little sticker, for example, or something, or some chip. They may ask you, hey, look, if you have this chip, you could basically skip the entire line. This is another example of where a priority queue would make sense. So what happens is, in this case, you would remove the person at the front of the line, and you would change their priority so that they can get back to the front in the future if they come back in. So these are a couple of ways you can view a priority queue when you do the insertions. Now, I'll give you another analogy in a moment, but let me just keep proceeding. First, are we okay with inserts? So all I'm saying is the one that's going to go in, I'm going to imagine I have a collection of elements. They're all going to have different priorities. It's just going to go into priority queue. This is just a visualization for you to help you connect it up with a queue. So you can imagine it like somebody gets a skip in the line if they have a higher priority than another person does. That's the way it generalizes. Now, if I want to do this is about the equivalent of a peak operation, is so-called min here. So what I do is I return the element with the minimal key, and null if the priority queue is empty. So all I'm asking is you just return it, but you don't remove it. So I'm just taking a peek at my priority queue, and I'd say that's the one with the minimal key, meaning it has highest priority. I'm not going to remove it though. That's what remove min will do. So what remove min will do is quite like in my picture here. If I were to say, if I wanted to remove min, I would get rid of this one, and I would say, hey, look, I'm just going to return this. So I'm just going to return that right there. And now this would become, hypothetically, the front of the priority queue. It depends on how you implement a priority queue. That's why this visualization may or may not be very useful. So that's the remove min operation. Is empty. It just returned true if there's elements. Sorry, there are no elements. It's Wednesday. If there are no elements, you return true. However, if there's at least one element, you return false. It's just a way I can use. So for example, if I want to dump out all the elements in the priority queue, you may want to have like a while loop, for example, to do something like this. You can use is empty to check if there are in fact elements. Another useful thing is to know the size, as in the number of elements in a priority queue. These are pretty standard operations. They may come in different names, depending on what you encounter. But are we okay with all these main operations here? So I want to give you another way to think about a priority queue, because like I said, I mentioned that this isn't necessarily the most useful way of thinking about a priority queue because it looks like something just like a queue. That's one way why I'm drawing it for you, is I want to remind you of what a queue is like, where I dequeue and enqueue elements, but I don't have priorities attached to them in this case. If you want to think about the priority queue as a queue, you would make it so every priority is the exact same. So a way that this is a way I like to think about a priority queue is, instead, I want to imagine I have a bunch of elements. And this is my priority queue. It's just this bucket here. So what happens is when I do inserts, I just put it into the priority queue. So what I'm going to assume is like the blue ones are the most important. The red, actually, let's go with the red ones, because these red ones look like a warning or something. These are the highest priority ones. We'll say the yellow ones are the next highest, then the greens, then the blues. So imagine I start inserting these elements into my priority queue. I'm going to insert them into my bucket. So now I have the blue is in there. I'm going to put a red in there. If I were to go remove min on this priority queue, just think of it as a collection of them. Which one should I remove? The blue one or the red one? If I remove min, which one was the highest priority? It's the red one. Yeah, so I would remove this one from the priority queue. This is what I would return. If I just insert each one of these, the next highest priority one would be, by the way, the yellow one here. So if I were to use the min operation, what would happen? Would it remove this from the priority queue, or should it just return me like what this is? It should just return this, right? Yeah, just return it. Don't remove it. It's just, I'm taking a peek at the priority queue. It's perfect. So if I did remove min, however, it's gone. It's gone. It's gone. If I were to do, if I check the size of this, I would tell you that there's 3 elements right now in my priority queue. And it's, of course, not empty. So if I keep doing remove mins, I should get a green one. It's gone. Here's a green one. It's gone. And I do another remove min. The blue one's gone. The one with the highest priority. So in my convention I'm selecting here, the one with the smallest value will be the highest priority. So when I say the minimal key, when the smaller the number is, that's the higher the priority is going to be. Well, there are ways you can always define it so it's the maximum. You're going to see that I'm going to give you another way you can think about it in that way. Yeah, it could be min or max. You just pick a convention. So in my case, I'm going to show you how to do it with just a minimal value. But I'm going to also show you later, just to give you an idea. You're going to see how I'm going to do this. It's actually just, you literally just reverse everything I'm going to do. So if I give you min, it's very easy to get max. It's just everything, you just flip everything I just described to you in terms of like inequalities in the pseudocode. So we're doing this also for another reason that's going to be relevant later on in this course. But yeah, are we all good with this? So you can view it like a queue where people can shortcut in front of other elements, or you could see it as like just a collection of elements like this, and you just put them in there. Okay. So let me just get over to the other board over here. I want to do a basic implementation. So I want to describe to you how I can get a priority queue just in a way that I would describe it at this level. Yeah, triage is actually, like, that's pretty much the natural example. If you want to do things in a medical setting, if they ask you for scheduling in a medical setting, they very often want things that look like a priority queue. And then it gets a little bit more complicated from there. But anyways, so I wanted to do some basic implementations and just compare and contrast. Now, because you've probably seen how you implement a queue using an array, I want to focus instead on how I can use doubly linked lists to implement a priority queue. So what I'm going to do is I want to consider 2 versions. I want to consider a sorted doubly linked list and an unsorted doubly linked list. Now, just as a quick reminder what a doubly linked list looks like. So I would have a head node, and in my nodes, I'm going to have a previous and a next element. So in this case, the previous would be nothing. Then I would have some element here. This would be where you put your element for the priority queue. And then, of course, you would have more and more of these elements, and so on. And then you'll have a reference to the rear of the doubly linked list. There is no reference on the end, but you'll notice that I'm going to have a next. So the next is going to point to the next node. The previous is going to point to the previous node. And you do this for each one. So like if there's a node here, it would refer to this one. And you have the same thing going on over here. So notice I just have pointers going both directions. So this is how a doubly linked list would look like in this setting. So just to clarify this part here, this is where your element would go. There's where your element is going to go. So let's think about this. Okay, imagine I want to maintain this doubly linked list so that the elements are sorted from highest priority to lowest priority, as in the smallest key to the largest key. So let's consider where I have the sorted version first. Now, the isEmpty, size, and min, they're all rather straightforward, right? If you really think about it, in the sorted version. First, if I sort them from smallest, so this is just sort. So maintain, so we're going to maintain sorted, this is sorted, maintain sorted elements in linked list. So we're just going to keep the linked list in sorted order from priorities smallest to largest, or most important to least important. So when you do this, if I want to do an insert operation, can somebody tell me what I need to do? We're keeping it high level here. I'm sure that you're familiar with what a linked list, what that is and how it works. So what would you do with the insert operation? Would you, like, for example, would you just stick it in the front? Probably you wouldn't do that. Instead, if you want to maintain that the elements are sorted in the linked list, instead what you would want to do is you would want to have it so that you traverse the linked list and you find the next available spot where the priority is so I would remember, like, say for example, this was like, say the key was like 1, 3, and 5, and I wanted to put in, say, one with priority 2, I would want to put it right here, right? So I would create a node, I'd put it right here in between these two, and now I'd do a little bit of surgery, right, to maintain all of the references, right? So you would traverse the linked list. And then you find the spot where its key in a new node is at least, well, it's technically the first spot. Find the first spot where it's less than or equal to the key of the next node, right? So I just go from left to right, traversing through my linked list. So I go to the next one and I just examine if my key is any greater than the one that comes next. If it isn't, then I better stay where I am and then insert here in the linked list. So if you think about that, what's the worst case when it comes to doing the insert in a sorted linked list? If I give you n nodes, what would be in terms of big theta or big O, if you want to think about it in big O? Yeah, it's linear, right? Perfect. So when it's sorted like this, you know it's going to be big theta n. Okay, if I want to get just the min, here's the great part about using this approach, and is that notice that the minimum key or minimal key is always the first node. So notice that if I want to examine or get min, notice it's right at the head of the linked list. It's going to be referred to it right at the head. So I can do that in constant time, right? Likewise, I can do the remove min. So let me go remove min. So remove min, you would just remove the head node from linked list. You remove it from the linked list, and you return its element. I apologize, it's a little small. So remember, all I do is I just remove the head. It's big theta, but big O, remember, if I write big theta, it implies that it's big O. So I'm just using it just to be a little stronger about what I'm saying. But you can easily write big O here, and it's no problems. So when I remove the min, it's constant time. Again, big theta 1. Is empty? Well, in a linked list, you can easily keep track of how many elements you have, or you could just check if that head node is null. So I can do that in constant time. And the size, if I keep track of it in a counter, there you go. It's constant time. So now, notice that this is pretty good. It's not bad at all. When I do the unsorted version, you basically get the flip of this, right? So I'm not going to write anything here because when I do unsorted, you'll notice I just literally, the trade-off between the two is that in the unsorted case, when I do the insertion, I could just put it right at the front. I could put it right at the rear, I just put it at the rear, right? I could just put it at the rear, or I could put it at the head. It doesn't really matter, right? Remember, just think of it like the bucket. So I don't really care about where I stick it, as long as it just goes somewhere in the linked list. So I just insert it into the linked list. It could be on the head or the rear. It doesn't matter. So I could do the insertion in constant time, in big theta 1, in the worst case. When I would do the min, however, notice that the trade-off, notice there's a complete trade-off here, is that because I don't have it in sorted order, now whenever I want to get the minimum, or even remove the minimum, notice I have to traverse the entire list in the worst case. Does everybody see that? So notice that if it's unsorted, like 1 could be right here, for example, or 1 could be right there, and I have to traverse the list. And if I find it, that's great. That should be what you should expect because it's already in the priority queue. Notice that I don't have any parameters for the min or remove min. I assume it's present. If it isn't present, then I return null. So in these cases, I have to bite the bullet, and I get that linear time for remove min and min. Fortunately for us, the principles I just described for is empty and size, they aren't any different. I can do these both in constant time, in big theta 1. So hopefully everything I just described to you is pretty clear. So I just want to give this to you as a basic implementation of a priority queue. So of course you can implement priority queues with arrays. A lot of the things I just described to you would apply in terms of an array. I just want to show you one example of a way I could do it. How do you do size in big O of 1? You keep a counter. So you just keep a counter. So you have a little variable that you keep track of. So as you do insertions, you're just going to increment the counter whenever you do an insertion. And whenever you do remove min, you decrement the counter. That's how you could do it. But yeah, the common trick when you're implementing linked lists, for example, that way you don't have to traverse the entire thing to count it. But yeah, no. So this is a basic implementation. Now this is pretty good. This is pretty good for small-sized priority queues. But what if, for example, I have like 1 million, or even 10 million, say if I have 10 million elements in my priority queue? Well, this might not necessarily be the greatest, but it might still be fine for maybe 1 million elements. But if you start getting to like 100 million, this is going to start getting a little bit it's not going to scale very well because it runs in linear time. So that means I'm going to have, in the worst case, I'm going to scan the whole thing. So instead, what I'm going to do is I'm going to try to describe to you a way I can implement a lot of these operations in a different way that reduce the time complexity. So that brings me to talking about heaps. The first, are we all okay up to this point? Give me a thumbs up if the eraser is my thumb, okay? So just remember, all I'm doing is now I have these priorities, and they dictate who who or what gets out of this priority queue first. Perfect, I see a thumb, we're good to go. So so we're gonna talk about heaps now. So we're gonna use heaps to implement priority queues. And the reason why you might ask, Dan, well, why? We're going to see. And you might naturally ask, Dan, what the heck is a heap? So let's talk about what a heap is. And I'm going to give you some properties a heap has. And then we're going to see how we can use a heap to implement a priority queue. So I just want to remind you first of what a binary tree is. Just a reminder. Because heaps are going to be... The heaps that we're going to talk about are special kinds of binary trees. So you've heard of binary search trees. I'm sure you may have heard of binary trees. But I just want to remind you, just to make sure everybody's on the same page. This is why I did this the other day. So it's an ordered tree. I could technically say it's rooted, but I'll just say it's an ordered tree. But yeah, it's an ordered tree where every node has at most 2 children. Has at most 2 children, where each child node is labeled as either a left child or a right child, and a left child precedes a right child. So that's the ordered aspect of this tree, is that I'm going to have 2 children. I'm going to assume that the first of my 2 children is the left one, then the right one. Those are names I'm going to give the children. So you might ask, Dan, what the heck is a heap then? So we're going to talk about so-called binary heaps. So a binary heap is a binary tree. It's a binary tree that satisfies 2 properties. So it's going to have to satisfy 2 properties. I'm going to give you these 2 properties. Now, the point of these properties is to make sure that we have something that maintains the rough shape of this tree, and that it also has the property that it's nearly complete. So when I say nearly, I'm using air quotes here. So I'm going to define what both of those mean. So I'm going to have what is called, so the first property is called the heap order property. The heap order property. So it works like this. For each node, and sometimes I'm going to call these positions just for the sake of convenience, because when we start talking about implementations of our heap, the nodes are going to be represented by positions in a structure. So I'm going to sometimes use the word position just out of convenience. So I'll just say for each node or position. Sometimes people like to refer to parts of the tree, like a node, as a position in the tree as well. So there's a couple contexts that's applicable. For each node or position, P, other than the root. Other than the root. The key of P. The key of P is greater than or equal to the key of its parent. So if I examine a node P and I check its key value against its parent, it better be that P's key is going to be at least Like it's going to be greater than or equal to the key of its immediate parent. And this is true for every node except for the root. So naturally you might think, Dan, what does that mean about the root? Well, the root has to have the smallest value for a key among the entire tree. So this is going to be rather useful for us. And the intuition I want you to think about when I say the word heap, think of like a pile. So imagine this collection here had a very special structure to it that looked like a pile, like a pile. And I want the idea is that I'm going to use this heap order property so I can use and grab the thing that's on the very top of this pile. So I just want to plant that idea there for now. So this other one is called the complete binary tree property. The complete binary tree property. It works like this. Is that a binary tree of height h, where levels I is equal to 0, 1, 2, all the way up to h minus 1. So I'm looking at the levels of my binary tree. I want to consider the first h minus 1. I want to include the first 0 all the way up to h minus 1 levels. I want to consider these ones. Have 2 to the power of I nodes. This is the maximum number of possible nodes at that level. We actually used this property at some point earlier on in this course. It was actually involving the decision trees. So I'm going to assume I want to make sure that all the levels except for the last one have this property. And the remaining nodes at level h are in the leftmost possible positions. You're going to see what I mean when I give you the example. So this whole thing is going to have nodes at every level, as many as possible, except for the bottom level. And on the bottom level, everything, all the nodes or positions are all going to be shuffled as far to the left as possible. If you think about it as a binary tree where I have left children and right children. So these are the two properties. Now, you might ask, Dan, why do these two properties need to matter? Let me draw the example here for you. And when I'm doing this example, I want you to think about the operations that we had for a priority queue. Okay. Oh, question. What do you mean by the key of P? Do you mean element? Key. So remember, I'm going to have so each one of my nodes in this tree is going to have an element that's going to be in it. That element has a key. So whenever I refer to key, I'm referring to an element's key that's going to be in that node. Yeah, there won't be multiple elements sitting in one node. There's just going to be one. So let me give you an example of one such example. So imagine I have the root being 5. Going to have a left child and a right child, 6 and 8. Then I'm going to have 7, 10 as the children of 6. For the children of 8, I'm going to have 12 and 11. And for the children of 12, I'll have 15 and 13. For the children of 10, I'm going to have 18 and 17. And for the children of 7, I'm going to have 14, and 22. So the first thing that should stick out to you is that this is not necessarily a binary search tree. Does everybody see that? This is not a binary search tree. Can somebody tell me why this isn't a binary search tree? I want to make sure everybody knows the difference between a binary heap and a binary search tree. So I just want to ask you, what would, like, this, there's something different about this. So yeah, 6 is greater than 6. So notice that, yeah, you'll notice that this actually is imposing a different structure than a binary search tree. A binary search tree, if you examine the node, its left child, all of the nodes in its left subtree rooted by the left child, all the keys will be less than it, and all the keys to the right of a node should be greater than it, right? So when you think about this, you have to be a bit careful, because remember, there's 2 properties that our heaps are going to have. Yeah, so in this case, notice there's only 2 properties. There's that, notice that I have this heap order property, so if I examine any one node, like say 8, its parent this has to be greater than or equal to its parent's value. Another way you can view this is that, notice that if I look at any one node, all of the children or descendants of that node have to have a key that is greater than its. So notice I have 8. Notice that all the keys of its descendants, all of them are larger than it. But notice that I don't care about what the difference between the left and the right child and their values are, except for just this heap order property satisfied. So does everybody notice that? So that's really important for you to see, is that it really, like, it's completely oblivious to the fact that, oh, this is the left one, this one has to be less than that. No, it doesn't have to be at all. All that matters is I look at the node and I ask, okay, is this greater than or equal to its parent? Or in another way you can look at it is that if I look at this node, its children all have to have keys, at least it, right? So I have a question for you. Where is the element with the minimum key? So note, I've just drawn only the key values, but where is the minimum key? Where is it? Where is it in this heap? So remember, it's just a tree. I'm not doing anything magical here. Where is it? Where is the minimum key? It's the root. This is going to be a very important property for us. So notice that the root has the minimum or minimal key always. So that's the big thing I want you to remember. So remember I told you about a heap being sort of like a pile, and you imagine it like a pile. Naturally, the first place you'd want to probably start when you're collecting off a pile that's very easy for you to grab. Like say you have really long arms and the pile's really big, you just go, just reach over and grab it. The top is maybe the first place you want to look if you're looking for something, as opposed to knocking the entire thing over. And the same thing applies right here. So notice that the minimal key is always going to be sitting in the root. So what I described to you just now is what we call a minimum heap or a min heap. So this is what we call a min heap. So the properties I've just described to you, these all apply to min heaps. There's another variant of a heap we're going to talk about maybe next class or the class after that, called a max heap, where in a max heap, the relationship is flipped. So in a max heap, I'll just acknowledge this right now. So in the max heap, I just change around the heap order properties slightly. So before I have it where I said that no for a node other than the key. So notice over there, the min heap, it was greater than or equal key to. No, let me just expand out. It's easier for me to do it this way. So max heap, let's see. So I'll just say for each node P other than the root, the key of P is less than or equal to the key of its parent. So if I told you I had a max heap instead of a min heap, like suppose this was a max heap. This isn't, by the way. Where would be the maximal key or maximum key? It would be in the root. So it would be in the root the same way we had it here for the min heap. So, okay. So I'm going to be talking about insertion either today or next class. But so I'll be talking about how you modify this heap and some ways we can implement it. But I just wanted to make sure we know what this means. I'm going to give you a property. I'm going to include its proof in the notes, just for the sake of time. A very important property here that I want you to be aware of is the following theorem. And its proof actually isn't that bad, really, at all. Actually, it uses a very similar technique to the one we used actually when we were establishing a lower bound for our decision trees when we're doing the sorting lower bound. I did like applied logarithms to both sides, and I did some little trickery there. This proof is very similar to that one in that sense, but it's not exactly the same. But the proof is kind of cute. So the height h of a heap T with n elements or entries, however you want to think about it, or nodes, h is equal to the floor of log base 2 of n. So the height of a heap, when I give you n elements or entries or nodes, however you want to think about it, is logarithmic. So the question I have for you is, okay, well, what's the floor of log base 2 of n in terms of big theta? Well, it's log base 2 of n, like it's big theta log base 2 of n, right? Or just log n. So this is the whole game plan, and this is a very common strategy in data structures, is that if I give you some properties, so I've defined this heap for you, and I prove this property about the heap. The goal is to have it so my algorithms that implement the operations of my ADT, as long as they maintain the two properties that I had over here, the heap order property and the complete binary tree property, as long as I have these two properties, I can guarantee you that the height of this heap is no more than the floor of log base 2 of n. So we're going to make sure we always keep those two properties in order. And if we can do that, we can guarantee that the height of this is always going to be big theta of log n. So does everybody understand the game plan? So when I do this, when I do operations like insert, remove, min, and so on, I'm going to make sure that it does not destroy those two properties I have over there. So this is a very common and powerful technique, so-called I'm preserving the properties of the heap by every time I make a modification. Some data structures you don't do this. We'll talk about one example of that in this class, just as a variation of this idea. But this is very common strategy in data structures, that you have properties that your structure has, and you design the operations so that you maintain the properties of the structure so that you can still maintain some special property it has. So it's like if I told you my dog has a tail and 2 ears, I want to make sure that my dog always has a tail and 2 ears every time I do something with the dog. You would never want to have it, obviously, where you cleaved off an ear of a dog. That would be terrible, and that's a terrible thing to happen. But it's very visual, right? You would not want that to happen. The same idea here with my heap. I do not want to have it where the height just gets out of whack. And I can guarantee, if I have those two properties, that I end up with a heap and its height is logarithmic. Does everybody understand the plan? So we want to maintain this logarithmic height, and to do that, I need to maintain those two properties I had, the heap order property and the complete binary tree property. So now I want to talk about something briefly, and then we're going to wrap things up here today. I just want to describe the starts of the next implementation we're going to see. So I'm going to describe a very simple way we can implement a heap. It's so simple, it's beautiful. And as soon as you start seeing things this way, it's like, wow, that's actually kind of neat. I didn't know you could do that. But watch this. Watch this. So I'm going to show you how you could implement a heap using an array. So we're going to talk about an array-based implementation. Now, I must stress that, as I said, this thing is a tree, so you could implement it as a linked-based structure, and many of the things I'm going to describe in this next couple of lectures are all going to apply. But this simple way of implementing the heap, this is one that I would think that's rather important that you see it. And just for the sake of purpose for my arguments here, I'll come back to it later. I'm going to assume that you always know how many nodes you're going to need for your heap or elements. I just poked the turtle. So I'm going to say we can represent a binary tree with n elements using an array. So I'm going to assume that n is known at this stage. With n elements using an array. Sorry, I was getting a little ahead of myself. Using an array. Consider an array A of length at least n. Then we can compute positions. Then we can compute the position. Let's say the position. Like I said, it's going to have a meaningful case here. Position of P using a function f as follows. In an array, this is going to actually be way simpler than I'm doing it, but I'm just going to keep it general because you can use the same idea when we talk about just a tree, like a linked-based structure. So if P is the root, then we're going to say that the position of P in the array is going to be 0. So it's going to be sitting in the very first position of the array if P is the left child, then I'm going to tell you that if P is the left child of Q, say Q is another position, then F of P is equal to 2FQ and then naturally I need to describe to you what a right child is if P is the right child of Q, then F of P is just going to be one position higher, 2F of Q plus 2. And if I want to know where so if P is not the root, if I want to find out what the parent is, I'm going to compute it this way. If P is not the root, then the parent of P is located in the floor of f of p minus 1 all over 2, rounded down. Now I must stress that f of p and p, when you're using an array, is going to be, like if I told you position I in the array, you could just simply replace what I have right here or there with just an I. So I'll do an example next time. And that being said, I'm going to stop right here for today. So when we come back, I'll show you an example. I'll include it in the notes if you want to read a little ahead. And that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.